HP printer. And I could work on the colors and make things more legible, and I really need to. But everything I've been doing, and everything I'll show you today, is work in progress. Priorities really are such that none of this is mainstream. But I am working more than ever in color court. I really like it. It's the first thing I'm going to talk about. The i21SL is the latest version of the chip, and it's been back for 2-3 weeks. And then I've still got dreams about internet.
How do you tell the difference between an I and a 1?
No,
Context.
it really doesn't matter. But I will be designing a new character set that makes that clear. I've got a utility which does that.
What kind of keyboard do you use?
It's a normal PC.
Work in progress.
All right, here's a screen full of color force. Good. Dumb machine.
Move machine closer to
Further away? Closer. The first thing I want to talk about is the bottom line. I have a paper for formal, which I will give you Tracy of, and that is the new command line. I couldn't demonstrate.
There's a screw thing that tightens.
I couldn't conveniently demo this because I don't want to drag a computer here. One day I'll get a laptop. But I've got a command line at the bottom of the screen. And I have never heard anyone else mention this, so I mentioned it to you. It scrolls from the right. Normally you type characters starting to the left and they move across the screen with a cursor. This doesn't. This characters appear at the right and they scroll across to the left. There is no cursor. It doesn't need it. The advantage is I get a whole line of history as to what I previously typed. No need for vertical scrolling. And the beauty of that is that I don't interfere with the picture on the screen. Whatever is up here stays there. It's just the bottom line reserved for my scroll. Before, I had 2 lines at the bottom, a little window in which I typed from the left and things scrolled up one line, I got one line of history. This is even better because it turns out I get more history this way than I did that way, and it uses less space. I think this is a great example of conserving the valuable resource of pixels on the screen. It's a resource that nobody cares about. I saw an ad in one of the internet magazines for a browser. I'm not sure what it was. I don't know if it was a browser, but it was a browser frame you could put up on your screen, and you had customized boundaries and boxes and dials and things. And that's about the pace at which the world is going. They're willing to give away the edges of their screen because they're useless. I saw another example. It was some application I was working on, something to do with Word or some kind of word processor that had, I think, 3 layers of frames. Was in the middle, about 1/8 of the screen was available for the text that I was the result of coordinating an ADA.
You sell advertising in frames.
Yeah.
That's for all the money.
It's ludicrous that they're willing to give away most of their 1024 by 800 pixels. And I'm not, so I've got better things to do with the screen. Now this, I saw a word earlier, marker. Is that NC or something?
Yeah.
So remember's gone away. All right.
Yeah.
I'll use marker. It's shorter anyway. It's tired of the long word. Here's a little application that fills a table, amusingly enough. I'm filling a table with temperature to 3/2 power. And this is the code that does it. The thing of note is the word fill is referenced inside itself as a jump back to the beginning of the definition. This is relevant to the high-reveal debate that is currently raging on the Standards Committee, which all of you are familiar with. Hyde used to be called Smudge, and I guess the great debate is whether to change the name. It's not clear to me. But anyway, I've given up on that because it's just too complicated for ColorForth. ColorForth is brutally simple, or it will become brutally simple. And this construction of a conditional or any kind of a jump back to the beginning is very convenient. It saves a lot of begins and swaps and confusion. Flow of control, I think, is clearer here. If the condition is true, you go back to fill. Otherwise, you jump to them and jump out. So that's all this is intended to illustrate. Also, the fact that every word here has a space preceding it that describes exactly what the word is supposed to do. In other words, there's an invisible character here that turned this word blue, which means it's a comment. And the next word is also blue. This word is white on the screen, black on the printout, and is executed. This word is being defined. Now remember, the word remember says that the next words you define are going to have the does behavior of remember. And a word being defined is red. So I'm defining it at this point. Having done that, I use a colon to switch the behavior back to that of ordinary colon definition for all future words being defined, of which there's a bunch in block 65, and then this word TA. Now, TA, the body of the definition is in green and ends with a semicolon. And in this case, TA is a constant. That is the way I define constants on the I-21. It's the most efficient definition that avoids this long word constant that doesn't convey a whole lot of information.
Hi. How the 65 between the 65 below between colon and TA? That is, colon in ColorForth, does that mean the beginning of a definition?
No, that's the specification that future red words are colon definitions. I'll show you another example of variable.
All right. So the TA has within it that code saying that it's now a definition.
He called
that red word.
At
red word. Right.
At define time, the address provided is that of colon, as opposed to that of remember.
I'm going to type a red word.
I'm using the function keys.
Okay.
I've given a color to each function key.
So
and they all-
remember and colon are like states.
Yes.
Okay.
So this acts like a constant.
That's a decimal constant too.
Yes. I'll show you a hex constant later. The hex constant will be cyan. But this code is not meet the absolute standard. The word if here should be black.
Right.
And then should be black, because those are words executed, not compiled. And likewise, outside this definition, I switch back to black and execute things. 100 fill executes the word, it forgets everything here, and end marks the end of the block. Other than that, this code is probably very self-explanatory. Here is a -1 plus, which is the way I do things. I do not have a subtract. This is partly experimental. I want to decide whether subtract is an essential operation to have. The answer is no. If you're doing comparisons, use an exclusive OR. If you're doing arithmetic, use minus numbers, plus. Very, very occasionally you need to actually do a subtract. I think I've done an example coming up. This is code that's actually used by that word. This is a square root, which I'd like to talk about as a square root, apart from as an example of color for it. Here's a cyan constant, 1FF. One of the things that pleases me most about color for it is the colorfulness of the screen. It is really dull to look at a black and white screen. And this is fun. And that's why I'm willing to add more colors. Here's an example I want to show you of where I want to put in more colors. I'm not there yet. Now, the first couple words here are fixed point arithmetic. I am defining this as the number 1 plus, or 1 dot. This is the unit 1. And it's got 5 bits, 9 bits, 512 is 1. And to multiply two fractions, you do a 1 star slash, which gives you another number scaled by 512. To do a divide, you do a 1 swap star slash. This is not the most efficient way of doing it. You should do a multiply and then a shift. This is the easiest way to do it if you just want to do a two fraction multiply. And I use that in square root. I'm taking the square root of a number near 1, near 512. I'm getting a number scaled the same way. You do that by basically taking 1 minus 1/2 x. You get the square root of 1 plus x. And then I do a Newton-Raphson iteration to get more significant digits. In this case, I only want you to do 1 iteration. And now I've got a square root good to 9 bits, if not more. Very cheap, quick and dirty way of getting some square roots. The reason I wanted a square root is I want to take t to the 3/2 power. And I do that by taking t cubed and the square root of it. And the cubing part is just root star product. And that falls into square root because the headers are elsewhere. And I'm very fond of this style of having a couple of words cascaded together, one falling into another. It's in effect multiple entry points in the same word.
Shame on you.
And likewise, I get multiple exit points as I had before in the previous word, where I can say if fill semicolon, in effect that's an exit point, and another exit point. So semicolon does not mark the end of the definition. The end of the definition is marked by the absence of any more green words. Now here, this 1 minus 1 plus here is an awkward way of computing a number. I think this number 511, and this is not the binary subtract operator, this is the ones complement operator. So this almost makes this into minus 511, but not quite because I have to add 1 to it first. Now, my current thinking is, if I made this yellow, it would be executed as compile time. And the result, which would be on the stack, would then be compiled as a literal. I've been worrying for a year or so about how to do that, because I didn't want to have to say lit as an ugly word of no meaning, to say put the literal on the stack into the definition. If I make this yellow, the stopping of yellow, or the switching from yellow to green will perform that function.
I have a question. All of this stuff here it's constants or stuff that can easily be determined is only affecting stuff that you're putting on the stack during the definition of it. Why don't you have the compiler figure out when it would be a good time to inline stuff like this?
That's what I'm trying to avoid, because the compiler has to figure it out every time it compiles. Whereas I can figure it out once and for all and be done with it. Now, I'm planning on compiling these little applications every time I use them. So my dictionary will always be very small. I won't have any need for vocabulary. And I want the compile to be very fast. And decisions I can make at, we don't have a name for it, at programming time are cheaper than decisions made at compile time, which are cheaper than decisions made at runtime. And besides, it adds another layer of color. Now, if I have a word in here that is not a number, like it's an operator, if the operator is yellow, it will be executed just like it would if it were white. But I think it'll be more colorful if I make it yellow. I guess not.
As a functional matter, you get the function key, and then that function, that color applies until you get a different function key?
That's the way I used to do it. That's kind of the way I'm doing it now, and I don't want to. I want there to be an explicit character, space character in front of every word. It isn't. I'm not clear on how to use the space bar. The space bar at the moment generates a space which has no color information. I'm tempted to make the space bar generate white, which is perhaps the most common use of it. A little bit vague. These things change from week to week. It isn't hard to change things. Here's another block. These blocks are 256 characters long. In this case, there's no end. It falls off the end and goes into the next block. Keeping things arranged by blocks is convenient in that I've got the whole thing in front of me at one time. This is, okay, here's a comment temp, empty 65 load, variable. Here's the use of variable. Now to specify the following words are in variables. And here's two variables, age and number. So I can define a bunch of variables in a line without repeating the big long word variable. Then I switch back to colon and start defining colon definition. Another hex constant. Here I'm defining origin and hstore and h. This is a little compiler. I'm compiling stuff into memory. What I'm compiling is actually it's a spreadsheet. I should go back to what I was going to talk about because I'm getting ahead of myself. So I've mentioned command line and hide and reveal, and now I'm off on the spreadsheet. This is the code for spreadsheet. There's actually a few more lines in the next block, but this is what does all the work. And let me show you what a spreadsheet is. In the case of color mapping, black does not show up well on top of blue, but it does show up well on top of all other colors. Here's a bunch of numbers. These 5 numbers describe this set of curves. These are the IV curves from the LG process of the current chip. These 5 numbers describe these curves. These are the N transistors, these are the P transistors. Now, you can't quite see it, but around that number is a ring, indicating that is the number which will alter if I push the arrow keys. Right arrow will move the ring to these other words, and up and down arrows will increase and decrease the values stored in that little box. So I can sit here and adjust these parameters and watch the curves change. There are dots in these curves that represent the measured values, and you can't see them, but you can on the screen. For one block of source code, I have a very convenient method of displaying numbers and adjusting their values. Every time I change a number, everything on the screen is updated. To me, that's a spreadsheet. I guess maybe spreadsheets are much more elaborate than that. Let me show you the source code.
Are you curve fitting, or how are you drawing those lines?
I am adjusting values
Drawing
manually
lines.
in order to make curves fit the data class.
Okay, you have other code that actually draws the lines.
Yes, there's a word I call to draw. And
That's the function taking the in at our in.
that uses the web. I'll come back to this picture in a minute. So this is the source code. And this has been on my mind for a long time. I'm very pleased that I was able to do it, and I'm very pleased that it was as simple as this. But here I'm just putting up some color backgrounds so that I can distinguish some of the numbers, color code the numbers, if you will. In principle, I have some labels up here too, but I'm not. This block, these are fourth words. And this block is interpreted. And as these words are executed, they execute a version of dot that puts out a number on top of that. So the location of the word indicates where the word's value will be displayed. And the color of the word just gives you some hint as to what its meaning is. And it's very easy to edit a block like this to represent the data as I want it to appear. Just define a fourth word box in your spreadsheet, and everything else is automatic. This is the word ID that actually draws the ID curves, and then N marks the end of the block. So you see everything on this block above the N on the display. And you see that there's a correspondence between those numbers and where they appear on the defining number. So far I've constructed 2 of these interactive screens, and I figure I will do many more. Originally I'd wanted these numbers to be right justified, and I picked the word size so that they would line up nicely on the right. In fact, I never got around to writing a right justified number output word. So they're left justified, and it doesn't really matter. I'm not motivated to change it. That is color code. And there's probably enough said about it. It keeps evolving. I'm using it in the context of chip design. Chip design's got the priority. I add features as necessary to facilitate my work. Kind of guiltily, because doing the spreadsheet thing has made it easier for me to do some curve fitting. And you have to be careful about making it easier because you've got to have a payoff. The payoff is this. The I-21SL came back a few weeks ago and almost works. This was on the LG fab line as opposed to the HP. And I've spent 5 years practicing for HP. And it's the first time I've done LG. The processes aren't that different. But they're different enough that a chip which worked for HP didn't work for us, for LG. The question is why? And the answer is the ID curves. I've probably showed you these before. They're very similar to all other ID curves. There are 2 changes I made. One is the slope of this line. This is a curve that curves for 5 volts. And this curve is much flatter for 5 volts than it would be for 4. 4 volts, curve would go over this way and then down. The 3 volts even more stronger, much stronger horizontal region before it bends down. Now, if you're familiar with the textbooks, they show curves that look very different from this. They show curves that are flat and then coming down. And that flatness is a lie. This is the shape the curves have. N's and P's. This is all 1 tile wide N transistor. This is a 2 tile wide P transistor. This says that the ratio of N to P is larger than 2 to 1, than 1 to 2. It's 1 to 3. And that's no surprise, because this ratio is a little bit vague, and it's process dependent. But this disparity is extraordinary. And again, the reason for it is temperature. We measure these ID curves because I didn't trust HP to measure them for me. I don't trust LG to measure them for me. I want to know what they really are. So we've got a little bit of circuitry on the chip that lets us measure the curves actually are. And the measurements come out much flatter than this also. But when we measure the transistors, they're hot because current is flowing through them. Heat is being deposited in the channel of the transistor in a very small area. So these transistors are running 100 degrees above ambient. And the resulting curve, if they were running at ambient, would be this. When I take out the temperature effect, the curves increase by about 50% AC and transistors. A huge change. 50% difference than I had assumed in designing the chip. And this effect is unknown to almost everybody. Really, among the first. Much good negative. The reason is everyone measures their transistors the same way by putting current through them and getting the measurement of hot while they're hot. Now, this has been hinted at in the literature. Some people have said we know we're measuring our transistors when they're hot. What I've never seen anybody do is convert the curves back to what they would be if they were cold. When they're cold, they're much more systematic than when they're hot. I mean, if you take this 5-volt curve and drop it back to hot, you get a large correction, a much smaller correction on 4 volts, and virtually no correction at 3 volts. Because the amount of energy you deposit is proportional to voltage times current. And you cut the voltage in half, and you go from significant effect to negligible effect. A relatively negligible effect of P transistors, since their current is half that, less than half that at the end. So I was pleasantly surprised to see such a large effect. And it accounts for all of the observed disparities we find in the chips. For a long time, we've been plagued by circuits that would work at 3 volts or 4 volts and would not work at 5 volts. And nothing I could do would make them not work at 5 volts. Doing this, they don't work at 5 volts.
In the simulator you're talking about.
Right. So I feel we've reached ground truth at last. I think last year I said I thought I found an effect which would account for this. And I haven't. Conceivably I'm wrong here too, but it looks good.
It doesn't seem to be comprehensible that the chips are actually running 100 degrees after
The chips aren't. The chips are running 3 degrees hotter than that. But the transistors, in a very small region, a very small transistor, is burning hot. And it gets hot almost instantly. As soon as I turn on this transistor, temperature pops up 10 degrees. If I leave it on, it'll pop up 10 degrees, 20 degrees, 30 degrees, 80 degrees.
How do you measure that?
You look at the way it responds.
Other than that, do you have any way of
Yes, but I don't have a picture, mostly because I forgot. But we have circuits on the chip. We have an oscillator on the chip, which I can switch from one configuration to another. And measure with the on-chip counter, measure the period of that oscillator. And I can display the period on the screen as a spectrum. Color capabilities. And I can get multi-line spectra of 1, 2, 3, 4, 5, 6, 18 so values. And if I adjust these curves to fit those values, I determine the temperature. The temperature of a transistor cannot be measured. It can only be inferred. We've thought of a lot of ways. We look at it with an infrared viewer. But the resolution is so coarse we would just get a blur of where the transistor was. I have no idea what the temperature is. Using the simulator, we are seeing things that are unobservable. And this harkens back to quantum mechanics, where all of the interesting things about quantum mechanics are deemed unobservable by Heisenberg.
You had certain temperature is a bulk effect. Temperature is a bulk phenomenon.
That is right, but we have some 6 million atoms in part of the transistor that heats. And that is enough to be a temperature effect.
6 million is full.
No, it is also very interesting. I have implemented this temperature effect several times and gotten it wrong every time except the last one. And the characteristic is, and this is useful for any of you who want to control ovens, the phenomenon of temperature rise is distinctly different than the phenomenon of temperature fall. Temperature goes up because you're pumping heat into it. And as you pump heat in, there's a very simple proportionality with temperature. Heat is proportional to temperature. The more heat you add, the higher temperature. It will reach an equilibrium at an easily calculable point. If you stop putting heat into something you heat it up, it will cool off by diffusion, which is a 1 over square root decay of temperature. It'll take much longer for it to cool off. Now we've observed some effects of these transistors, with these chips, that were totally inexplicable until now. The fact that if you in fact put 4 instructions in the same word, as we can do, they wouldn't work. If you put one in each, if you put each one in separate words, they would work just fine. What is different from running these instructions in quick succession as to running them delayed by 40 nanoseconds?
Besides the transistors.
They get hot. And that says that in 2 nanoseconds, the temperature did not decrease substantially. So it would ratchet up. You get a clock pulse and it goes up, and then 2 nanoseconds later it goes higher. And after 4 of these steps, you're 20 degrees above ambient. And things are acting differently than they did when you were cold.
Can you make transistors that have like LTAs with a high and a cold side?
I don't know. I wish.
Yeah, those are just
This is a this is a problem, but it's also a feature which we should be able to exploit somewhere. So far, the only thing I've come up with is it's very difficult to reverse engineer this chip if you don't have the proper temperature behavior of your copper. And of course, no one does because they don't know about it.
Have you noticed any effects with like cooling the chip down and starting the cooler temperature, or does this stuff happen so fast that the ambient really is sort of independent?
It's very hard to see anything. It turns out if we cool the chip, it works better. If we heat it works better. The design point is the worst part. But I'm hoping this will elucidate that.
How can we see this effect doesn't affect commercial CPUs or not?
because they have about a 500% margin that I don't have. So they wait a long time for these effects to dissipate before they execute that instruction. And this is particularly dramatic with things like gate arrays and programmable gate arrays. They're running so slowly, they're so conservative that they never come to this.
Now that you know about it, what are you going to change to make things work?
I'm going to do what you always do. Make the transistors bigger. It's a sort of a knee-jerk reaction to anything. You can fix it by making the transistors bigger. The only thing this really tells me is which transistors and how much bigger. But not knowing that was absolutely critical. I just had no idea what was going on.
So what percentage of transistors can raise?
12 transistors out of 16,000.
Looks like
So, 1 in 1,000. Yeah. There are critical ones that generate pulses.
In that case, we'll
Small error down in the middle. Another effect we observed. We've got some chips in which we can, in fact, put 4 instructions per word. Those are the chips with particularly good margins that just happen to work. We can run all kinds of test code and those chips work just fine. But if we run the browser, it doesn't work. The browser only permits us to pack 20 to 50% of the instructions before it fails. The question is, of course, why? The answer is a browser does a lot of in-page DRAM accesses. And those are accesses made every 40 nanoseconds. The test code is not so disciplined, and it might have more interference from the video. It might make accesses every 150 nanoseconds. So this is saying if you execute these instructions in rapid succession every 40 nanoseconds, the temperature still hasn't gotten down back to ambient before the next one comes along to ratchet it up, and eventually you're okay. Whereas if you intersperse page change DRAM accesses, it's running slowly enough, the temperature does get back to zero. So these are 2 calibration points for long-term temperature decay, which I can use to help with the model.
One thing you might try as an experiment, get some coroner. You know what coroner is, right? Fluid is young fluid. But it's not necessarily cool. They have stuff that's room temperature boils at 100 degrees C and all kinds of different things. But some of the relatively high temperature stuff is pour it over your part. The reason why I'm saying to do that is because when you're running the transistors on the surface, essentially, a lot of people think that it's having some depth.
No, the surface.
Because they see these pictures all blown up. But essentially, it is the surface. And if you have something on the other side other than air for the conducting to, you can transfer heat faster off the surface. Yeah, and it'd be interesting to see what happens with just a little bit of fluid over it, to see how much more you can get out of it. Of course, there is a disadvantage to that too, is because the little wires have a little bit more capacity. And some stuff with it.
We need to do some more measurements of different temperatures.
Yeah.
One of the problems is to measure the temperature. And this is the experiment, but since you don't know what the temperature was, we have no quantifiable effect. And the other thing is, I'm not sure that would help because the heat has to diffuse away from the transistor before it reaches the surface to be conducted away by the fluid.
But the actual hot part of the transistor, this is what I'm saying.
It's a couple microns down.
It's essentially the surface. Because that's where it's right below the gate. That's the more resistant part.
There's a couple microns of silicon dioxide above it.
Oh, that's true, yeah.
And we got more transistors a couple of microns away from it.
Yeah.
So saying that a transistor is virtually isolated after the heat.
Oh, that's true, yeah.
And you get these confounding effects. But again, if you put your hand on the package, you can't perceive any temperature. It's only a couple of degrees above average package. because of a huge thermal mass. And we're dissipating very little energy. Now, the 300 milliamps that Mark mentioned is for the board. The chip is dissipating, I'm guessing, around 10 milliamps. It's very hard to measure because it's in the noise. And it's very hard to simulate because my simulator isn't accurate to these low energy levels. But one of our little challenges is to figure out how much energy the chip uses. It is almost miraculous. That's one of the few reasons for even doing this. As I have said before, the world does not want another microprocessor. We're competing with much better staffed and financed operations than ours. This is a fool's game. Don't design your own microprocessor, as I said the same years ago. But we got a shot at it because we are very fast, we are very small, we use very little power, and we're very cheap. And if you're not all of those things, you haven't a prayer. And since we are all of those things, we have a tiny chance of getting into the marketplace. How small? How small? It's unquantifiable. How small is it? How small? At 0.8 micron, it is 50 mils square. It's small. And we can make a factor of 16 smaller if we try.
So it's 1.25 millimeters in size.
This is 3 by 4 millimeters. The part we're occupying is 1 by 2.
That's about the size.
This is an amusing point. I found out from LG engineers that I've been running traces across this vast open space. And you can't do that because those traces are going to be corrupted at their edges by the fact that there's no metal around them to reflect the light during the massing. So I had to add more metal around the traces in order to try to reflect the content.
Yes, but I agree with the chips together with me, so you can look at the chip itself and the surface, how much place.
If anyone has a magnifier, 10 times magnifier,
Yeah, but it's in the table.
How much current should you do a transistor to get this kind of container?
Yeah, the HP process was 1 milliamp for an amp transistor.
1 million.
The LG process is 2 milliamps when at ambient temperature.
But in normal operation, none of the transistor
Yes, they do when they're switching. They go right to the max on a switch because they're driving a capacitive load that's got 0 volts. You have to charge that capacitor.
It'll be at 1 milliamp for about a tenth of an amp. And it will get hot for a tenth of an amp, and then it will. That won't get it up to 100 degrees. But only get 10 or 20 degrees, and then it will go away for a long time before I hit that transistor.
The big word now is IP, selling cores, sharing cores. Are you leaving interconnect paths so that you can work with other people?
That is one of the things on ITV's list of things to do, yes. It is difficult. People don't like the idea that this is a custom design. It doesn't have a high level description.
So you're going to have all description, doesn't have spice parameters and all the rest of the things that normal people want.
Now, I say with some justification that's a virtue, not a failure. But it does make it harder to sell at the core. I think we probably will because there are, it'll be a good core. We need to characterize it completely. And we we need to be able to provide the documentation, et cetera, that reassures everyone. And we will do that as we get the financing to do it, or as we get local interest. So far, we're producing chips to put in our own product. Plan. Okay. We have these processes on one of our chips at no extra cost. And you pick one of them, sure.
For a lot of DRD designs usually have triplet with voting logic.
Yeah, the voting logic is a horrible expense.
Yeah, I know.
It would have to be some kind of external program.
The only disadvantage of what he's talking about there is you still have to do it at wafer level. And the problem is once you figure out the package level and get it where you think you're going to put it in a system, the cost of testing has gone up by 100-fold.
Just because it makes more wires come out in order to do it.
Well, no, it just has to do with how you can test it once it goes into a system. You can't test it the same way you can when it's at a wafer. So that means whatever you test at wafer has to be very inclusive, catch everything that could possibly go wrong with that part. And it's difficult to do because when the cost of wafer testing, they don't want to run it at 3 different temperatures for instance. They want to run it at 1 temperature because that's cheaper. Because if they have to ramp the temperature up and down for each guide, then that's an extra expense. And you're running on a $2 million piece of machinery, this wafer program that has this high-speed tester attached to it, and the time on that machine costs money. And and of course the element of testing bad parts versus good parts. You test a whole wafer full of bad parts, you still pay the time of testing that wafer with a little bit shorter because you can skip the part if you know it's really bad. You say, that was totally garbage. Next one, that was totally garbage. Yep, this one's probably work.
Is it true that you only really need to test the outputs? I mean, if you had multiples, you could feed inputs to many chips and then just figure out more why the output.
Every single tester channel is an expensive item.
You're
talking thousands of
level.
You're talking. It doesn't
work.
Tester channels are thousands and thousands of dollars a piece. Each wire that goes out is thousands of dollars. So visualize thousands of dollars going out to one pin, right? So the cost of testing that is really how much it costs to get one wire brought out to it. The problem is that a tester channel, is a piece of board about like this on a PC board. It's a chunk about like that. That's one channel. So now there's a physical problem of attaching this much board to one little pin on a wafer probe that's this small, right? So you're saying, okay, why can't I just test more? Well, with his size die, he could easily have a wafer card that has two. Of course, there's registration problems in that, but he can have two. He can be probing 2 at a time, and the tester program normally would be. Most of the testers are big enough to handle that much data, and you just test 2 in parallel. The only trouble with that is it becomes very difficult to separate the good part from the bad part. You can't just if one of them fails, the result of the tester. Remember, the testers aren't saving a whole lot of information. It's basically pass-fail at that stage because it takes time to save the information.
Yeah, but one of what was just said is that you only have to have one set for the inputs. You can feed multiple sets on the input. It's the outputs that you have to maybe fuss with. Because some of the
most of the chip is bidirectional. It's not just inputs. You only have, on a typical processor chip, you maybe have only 15 inputs and maybe about 3 or 4 outputs, and every single other pin on it is bidirectional. So, those are IOs.
Yeah, I know.
Yeah. The other thing is the testers are relatively slow. You can't test those at speed.
No.
It's basically a DC tester. That's a hard one. I have on the last chip, the U chip, I did slow down the clock from 10 cycles, from 12 cycles to 14 cycles, or 8 cycles. And that chip worked very well. I don't know if it was that caused it to work or not. So to a certain extent, yes, we can slow it down. Without pretty good evidence that slowing down will help. I don't want to slow down, because that will kill our advantage. And that's
in this device, though, because you have DRAM for memory, you're so far off the chip's performance, except in a single word loop.
But I'm not designing it for DRAM. I'm designing it for on-chip ROM and RAM. And with on-chip ROM and RAM, I can run 500 MIPS flat out. Unfortunately, if we were to buy RAM from somebody who has a RAM cell and they were making it work on a chip, I couldn't. Again, people who design memories are conservative. Memories have got to work under all conceivable circumstances. And that means a factor of 2 or 3 in performance below what I want. I'm amazed at this conservatism. You see it everywhere. And it's gradually being squeezed out of airplanes. The Boeing computer-aided design tools are helping them get airplanes that are reasonably designed instead of fast field design. Same with ships. So we're moving in the right direction. But it is the industry is very conservative. I guess industries inevitably are.
Well, because lawyers inevitably aren't.
Product liability is a horrible.
Elephant fascists.
What, won't other people eventually run into the same problems that you're running into now downstream as things get pushed?
At the very small geometries, you get down to 0.12 micrometers. These effects are vastly affected. And the reaction is perhaps to slow the chip down even further, be more conservative. But I don't know, because I'm not
Copper helping?
I think copper will help. We don't have a problem, large problem with metal resistance. My design, my layouts are quite conservative in terms of the design.
Copper is mainly related to the light propagation. It doesn't change the capacitance all that much.
No, but it changes the R and the RC does.
That's right.
And that helps. The other thing is that the C can be reduced by going to insulate instead of semiconductor substrates. There's a lot of room for growth. I'm sure we will hit a couple thousand MIPS in a couple of years. It's not a question of technology, it's a question of corporate will and marketplace. Internet. This is an internet box, internet application, and it's a good one for a couple of reasons. One, it takes advantage of the high speed of the process, even derated by the DRAM, it's still running fast. We can run faster. It's a complex operation with a substantial amount of software, so we're doing something non-trivial. And it's a showcase application in that when you say internet, people's eyes light up. So it's a good field to be innovating.
Hello. If there are no more transparencies, are there more transparencies? Then maybe we'll elevate the mood. Right, everybody else.
Are you using any scan technologies at all now, or are you still testing it from the outside?
No, from the outside. The point is that the chip is capable of testing itself, and that's the way we're doing it. Provide simulated input from simulated memory and look at the outputs. In fact, we can let the chip run for a while and then he can come up with a goal. I think we interface the testing machine very nicely. But it's hard to tell the testing engineer that in the abstract. They hear asynchronous and they non-linear. So that's a buzzword that is be avoided. Well, no, it can't be avoided. We have to explain why our performance is better in some sense, by some measure, than in Intel's. And that's a word that makes sense. Oh, I think, I see how that could be. Internet, I think, is an example of this conservative mindset. There has been one browser invented, and that was invented by Mosaic, and everybody else is drawing copy from it. I was surprised to learn that Japanese televisions that drove Americans out of the market was copy license from RCA back in the 50s, 40s. That's the only color television that's ever been designed. Everything else is derived from it. This derivation is really mind-blowing. I don't believe the best browser has been written. I don't believe the best TCP/IP stack policies has been implemented. I think this whole thing can be streamlined and simplified, made more user-friendly. And I think you are the people to do it. And I want to toss out a suggestion. Most of the point of Internet is to get access to text. And there are huge libraries of books available on the Internet. And you can sit there and read Wuthering Heights on the screen if you want to. It has to be out of copyright. And nobody does. People do not find the experience of reading text on the screen to be pleasant. They'd rather read a book. It occurred to me that we are not using the screen properly. Human beings' English is read from left to right. This is text. And it's literally raster scan. You read this way and then you read. Now there have been languages, Hebrew perhaps, that are bootstrap-adonic. You read the text like this,
Sumerian.
6 lines.
Sumerian,
Ancient Greek, or the Chaldean. And we don't do it that way. But it isn't obvious to me that we shouldn't. It isn't obvious to me that it's very difficult to learn. And it is obvious to me that it's very easy to find out. All someone has to do is take a text file and put it on the screen this way and see if they can read it, to see if they can learn to read it. And I begged someone to do this and tell us what it is. Also, when you're reading a page of text, your eyes are engaged in saccadic motion, jumping all over the place. So when you're looking at a word, you're seeing the words that are surrounding you. And it helps you in comprehending what you read in ways that have not been quantified as far as I know. But certainly it is not a whole page that you're comprehending. It is a small region of text. So let us just display on the screen that small region of text and have a scrolling display somehow that your eye can remain fixed in the center of the screen and the text scrolls by instead of your eye having to scan the screen. Now, combine the two and say that we will have bootstrap-adonic text scrolling by. Now, the bootstrap-adonic scroll is more pleasant than a back-and-forth scroll. In particular, you don't need word wraps. It's just the characters that would flow back and forth over 3 or 5 lines or something like that. While your eye remains fixed in the center, and while you absorb the message the text is trying to convey. And perhaps the nicest way of doing it, if you can't read bootstrap-adonic, that turns out to be too hard. You alternate the lines and you let the text spiral in 3 dimensions past you, and the lines that are in the background sort of get dim, and the lines in the foreground are bright, and you're seeing not adjacent words, but you're seeing adjacent lines in the way we're kind of used to doing it, and the net impression on your eye is favorable. I have not heard of this being done, although a lot of things are done at university that I don't ever hear about. But I'd ask, let's try it. It's easy to try.
In speed reading, you actually do go sort of zigzag down the page.
Picking up a lot of peripheral.
Yeah, basically peripheral eyes.
So let's automate that.
Group. So you take maybe 7 steps to the third. You do it narrow count.
There are
narrow count, absolutely. That's why they are.
They have these little gizmos that shine a little light off the cornea of your eye, and they can tell where your eyes point. And basically, you can use that to control the speed of your scrolling. Basically, if you look more to the left, it says, I got to catch up with it. He's trying to feed more characters.
So that's one thing you'd have to do, adjust the scrolling.
And it can be just kind of more or less automatic by the rate that the guy keeps, he gets way ahead of the center of the scroll. And of course, if he stops completely, he doesn't know that he's stopped.
Technique to increase speed reading is you're looking at the screen and only one word comes up at a time at a very high rate. And they say speed read. With learning, you can speed read extremely quickly that way. I mean, the CIA uses that. They have to give people a lot of information. And it's just one word. Although if it was a word like A, I imagine there might be 2 words. But typically, it's one word at a time. Just flashing on the screen. Super fast.
I was about to say something similar, but I've seen devices where they, I've seen devices where they put one fairly short line of text, maybe about 5 words at a time, and you can have a button that'll set the rate. So I've seen those devices, and they help people learn how to speed read. It was something like that one. And so these things exist, they're one line at a time.
But they're easy to program. So we could try it.
There is a shareware thing demonstrating that one that's being talked about with a word or a few words at a small unit at a time, and you can get up quite fast and recognize what's going on in front of you, except one thing I noticed, there are some cases where the context is very important, and you might miss the negative in conjunction with the word, and might get an entirely different meaning. So it'd be helpful to have this particularly in front of you, but to have a little bit of the context around it too, to shift back to if needed.
I can see you wanting to flick back at something.
Right.
I don't see you wanting to flick forward.
With your eyes, not with your cursor or anything.
Except after you've gone back, you want to go forward to where you were. You have that.
Well, what I'm saying is about the throttle key and so forth, is when you release a throttle, and then you'll get the whole context with the area that you were just reading.
Put up the whole page.
Because then you put on the throttle again.
Kind of a little bit different vein. I have seen some experiments being done by, say, like artists experimenting in multimedia and that kind of stuff, where words are kind of given different meanings just by where they get positioned in time or something. I've even seen a simple version where, say, like poetry was done with words distributed around on the page in certain ways. And it kind of adds or alters the meaning.
Or change the meaning by
Changing the meaning,
color.
yeah, just because of positioning on a page or
I
something.
think the problem with English is English is the wrong language. Yeah, doing it in Chinese, that's no
The Chinese thing is beautiful, yes, that's
Can you do booster for that?
direction. It's no problem. Should we put some of this energy into voice rather than just looking at it?
Sure, but
Voice is
Voice
then you
is
can
slow.
drive. Then you can be
Voice is
the
slow.
No, I'm running your speech backward. You hear the devils.
There's a guy who does all these deliberate things.
I'd like to confirm that the CRT is brain numbing to read, but there's an exception. An LCD screen on your belly laying down on the couch I found to be almost as good as a book. The main problem to work on is the scrolling. which is sort of awkward to see the keyboard. But that, I got a really good feeling when I read the documentation to a certain program instead of ignoring it. I thought I learned something, seriously. And it wasn't a strain. Try it.
The lesson is, let's not be so conservative. Do not try some of these things which are easy to try. And I read a lot. I would be happy to read from the screen if it was more fun than reading from the paper. One of the characteristics of paper is that you know when you're getting to the end. You get to the end of the books, the pages kind of run out. It's a different experience, knowing that the author's going to wrap up the story in the next 10 pages.
Pages and paragraphs, also you do look ahead.
Yes. If you conceal that from the user, he doesn't know when the story is going to end. It might be more fun to read some of these things.
This is Polanski film where the plot wraps around the beginning.
I can think about wraps it up. We have to leave now.
I have kind of some slack with the administration.
I'm happy to entertain questions. I've
say 5 minutes.
had a lot of fun talking to you. Thank you.